I'm Jacob Nectarline, founder and president of Elementum 3D. Today we'll be talking about Elementum 3D's Navy SBIR-funded work to expand the range of 3D printable nickel superalloys for hot and corrosive environments. Elementum 3D develops, manufactures, and sells metal powder feedstocks for metal 3D printing or additive manufacturing. Our company's unique technology is called RAM, which is short for reactive additive manufacturing. In short, RAM is an additive chemistry that eliminates cracking during the 3D printing of metal alloys and makes the alloys stronger than they are without RAM. I'll get into a little more detail about why RAM works later, but for now, some company details. We were founded in 2014 and have 23 patents filed in a number of the most economically important countries, and are currently with more than 40 employees, of which 6 are PhD-level material scientists. We have a growing portfolio of complicated and ongoing SBIR and STTR projects, from which we have commercialized several products. We are located in Erie, Colorado, and have 2 locations in that city. We are planning to move to a new, larger facility next year to increase our powder production capabilities and inventory space. We also have more in-house printing capabilities with 6 laser powder bed fusion printers from EOS and SLM Solutions, including the new largest format system from SLM. Elementum 3D is ISO 9001 certified, NIST 800 and 171, and CMMC Level 2 compliant, as well as ITAR registered. The Navy challenge for this project is to rapidly develop high temperature and corrosion resistant 3D printable nickel superalloy materials. But why does the Navy need to 3D print metal parts? The Navy has a huge challenge in maintaining critical military equipment to ensure fleet readiness. Being able to readily source and ship spare parts for vessels and equipment is essential. Additive manufacturing can be leveraged to drastically shorten lead times for supplying parts for legacy equipment. To be able to print useful spares, the materials available to the process need to meet the high demands of the application. Nickel superalloys are needed for hot and corrosive environments because they have good high temperature mechanical performance and oxidation resistance. 3D printing of spares for high temperature systems has been very limited because many nickel superalloys cannot be successfully processed into crack-free parts. The sooner we can develop printable materials suitable for demanding naval applications, the better the Navy can maintain readiness by 3D printing high-quality, functional spares. The aim of this project is to use modeling tools to accelerate the development of 3D printable nickel superalloy materials. The expected transition targets are components and structures in gas turbine, marine exhaust, and high-velocity missile systems. The requirements of this program are to develop the solidification model for formulation prediction, identify candidate formulations, and then validate printability and material properties experimentally. The operational use of the high-temperature resistant alloys being developed through our modeling and validation strategy will first be for maintaining and improving legacy equipment. Then, the goal is to enable new, more powerful and efficient propulsion and energy generation systems along with weapons platforms. These applications are not unique to the Navy, and the materials developed using this approach have actually attracted quite a bit of interest from the Air Force and from gas turbine commercial energy production systems. Ultimately, we see passenger jet engines also benefiting from the enhanced range of printable nickel superalloy materials for heat shields, fuel injectors, and eventually turbine blades themselves. Alloy development for AM has historically been based on copying historical products. Our improvement over this approach is to combine simple models and our RAM technology to predict new alloys that are likely to result in crack-free printing. Our first product developing this approach was Nickel 230 RAM 1, a printable alloy 230 equivalent that was developed in under 6 months. This material is actually stronger than wrought alloy 230, with 60% higher yield strengths than the wrought material at 760 degrees Celsius. We were able to predict and fix the cracking problem by investigating the solidification behavior of these nickel alloys. Most cracking in metal 3D printing has to do with what happens when the molten metal cools. Solidification models give us an idea, based on the composition and cooling conditions, to which formulations favor a grain structure that avoids cracking. On the left, we have a RAM-free printed alloy 230 showing fairly large vertically oriented columnar grains in this colorful grain map that you see. Underneath that, we see cracking in the microscope image. When RAM is added, the cracking is eliminated, and the grain map on the right shows the smaller, rounder grains that are randomly oriented. The table below illustrates the consequences of the RAM additions at the microscale. The cracked printed alloy 230 without RAM actually has higher yield strengths at temperature than the wrought plate. But you can see that the elongation and the ultimate tensile strength are drastically reduced because of the cracking that has caused brittleness. With RAM, we have high yield strength, and we maintain the high ultimate tensile strength, and since the cracking is absent, we have even recovered most of the elongation capacity of the alloy. So it's clear that the RAM process completely changes the behavior of this material when printed, and modeling helped quickly identify the combination of RAM composition, the concentration, and the particle size ranges to test. We are currently in the second year of a Phase 2 base effort, and the Nickel 230 RAM1 has already been approved for initial commercial release at a TRL level of about 4 to 5. We've also started to apply the modeling approach to gamma prime containing nickel superalloys. These are some of the best nickel superalloys in terms of high temperature strength and resistance to creep. Creep is the resistance to deformation over long periods of time and high stresses at temperature. These alloys are used to make turbine blades because of these properties. It's something of a holy grail to be able to print turbine blades directly because of traditional casting processes that are very time-consuming, laborious, expensive, and have very low yields. Ultimately, the printing of these components will also allow for design improvements that dramatically improve the performance over castings. We have already seen some success in reducing or even eliminating the cracking in Inconel 738 and Rene 80, both of which are even more crack prone without the RAM additions than alloy 230. The table at the bottom shows the milestones and timeline for that Phase 2 work. We have already achieved the first 3 milestones, and we are working to refine the Inconel 738 and the Rene 80 formulations for the initial commercial release. By the end of Phase 2, we will generate full specimen and component level test data and performance ratings with the help of an industrial partner. And we are gathering feedback on the performance of the printed materials so that we supply to them for testing. We are looking to get into the Navy's Special Experimentation Cell to find and test applications for spare parts printed from our materials. This slide summarizes the key features, advantages, and benefits of our approach. It also outlines the advantages of the printed Nickel 230 RAM1 relative to the printed Haynes 230 alone and the wrought plate. With modeling, we estimate that we can reduce the cost and time needed for the RAM formulation development by 1.5 to 2 times. For the Nickel 230 RAM1, experimental validation showed that the material has a 60% higher yield strength than the wrought alloy and a 6 times higher elongation at break than the unmodified Haynes 230 that was cracking. Importantly, we were able to increase the creep life by 7 times relative to the unmodified printed 230 alloy. This is comparable to the wrought creep performance. Overall, we believe that the rapid development of easily printable nickel superalloys with the RAM additions has led to drastic lead time reductions for spare part delivery. A more robust supply chain is then useful for distributed production possibilities of additive manufacturing. The expansion of the range and capabilities of these nickel superalloys will open up new applications and increase the efficiency and performance across the board. I think it's clear that we've developed a great material that we're very excited about, and we're working to develop a few more under this same program. But ultimately, we need help transitioning this technology to make it broadly useful for the Navy. What we need are application targets, CAD files for printing components, and assistance in identification of any appropriate programs of record. Along with that, we're looking to expand into further Phase 2 and Phase 3 funding pathways. We already have buy-in from the Air Force Research Lab's Director of Additive Manufacturing And in industry, we are already discussing the use of this alloy with Northrop Grumman and Rolls-Royce for high-velocity weaponry and gas turbine applications. We still need transition advocates and application targets within the Navy, however. We believe the materials we're developing will be suited to applications in both commercial and defense markets. We're targeting gas turbine components like heat shields and fuel injectors in the commercial aerospace and energy generation markets. Applications in the commercial marine propulsion exhaust and cooling systems would also benefit from these materials due to their resistance to heat, oxidation, and corrosion. In defense, similar applications for gas turbines and marine systems are targets, but a major difference is the use of these materials in high-velocity missile systems that experience very high operating temperatures and oxidizing conditions. Elementum 3D's goal is to serve the commercial and defense markets however possible, just as we do with our aluminum alloys. We plan to accomplish this either through direct sales of our material to government sustainment facilities or working with contract manufacturers and large prime contractors as an integrator. From the start, our primary interest and objective has been to expand the printable materials library for additive manufacturing. Elementum 3D is an innovative small business focused on developing, manufacturing, and supplying production feedstocks for the commercial and defense customers. We also do prototype scale printing to support our application development activities and assist with knowledge transfer to contract manufacturers or OEMs at scale production. What we really need is to develop these defense markets further by really digging into the new materials for this program. To do that, we need Navy champions that can help us with the applications, CAD models, and testing requirements for increasing the TRL level beyond 4 or 5. As well, we also need inclusion in the right program of record so that we can really dig into things like specification development and full qualification, as we have with our other products. I'll leave you with one somewhat boastful but true statement. Prime contractors cannot supply printable, high-temperature nickel superalloys that are capable of competing in the defense application market because they don't have the right materials for them. Our new materials will enable the replacement of legacy components with drop-in spares with equivalent and, in many cases, better properties than the original component and still produced by those exact same prime contractors, just using our materials instead. Please help us make that a reality. Please don't hesitate to reach out to discuss your needs with us. We love learning about new ways that we can help customer deploy additive manufacturing in ways that improve upon the traditional processes. You can see from these various photos of printed parts that we're developing and have produced more than just these nickel applications. So if you have applications that require non-nickel based materials, you absolutely can reach out and contact us about those as well. We want you to succeed, even if it's not with us.